You must have seen objects that are cold, hot, very hot, etc. How can we say that an object is cold or hot? Let us discuss this with an activity. Consider 3 vessels of equal capacities. Fill the 3 vessels with equal volumes of hot water, ice-cold water, and lukewarm water. Place your right hand in the vessel with ice-cold water and your left hand in the vessel with lukewarm water. You feel that your right hand is cooler than the left hand. Take out the right hand from the vessel with ice-cold water and place it in the vessel with hot water, keeping the left hand in the vessel with lukewarm water only. Now, you feel that your right hand is hotter than the left hand. Thus, the terms hot and cold are relative. The lukewarm water contains more heat energy than the cold water. Similarly, the hot water contains more heat energy than the lukewarm water and the cold water. Let us see another activity. Take a small ice cube in your hand. Your hand is at a higher temperature than the ice cube. Then, the heat energy transfers from your hand to the ice cube. Since you are losing heat energy to the ice cube, you feel that the ice cube is cold. Now let us see another case. If you touch a vessel on a stove at a temperature higher than your body, then the heat energy transfers from the vessel to your body. Since you are gaining heat energy from the vessel, you feel that the vessel is hot. Thus, heat is an invisible form of energy which causes the sensation of hotness or coldness. At the molecular level, the heat energy of a substance can be expressed in terms of the mechanical energy of its molecules. Let us consider a certain amount of gas in a closed container. Heat the container at its bottom with a spirit lamp. As the substance gains heat energy, its molecules move randomly inside the container. According to the law of conservation of energy, energy can neither be created nor destroyed, but can be transformed from one form into another. That is, the heat energy supplied to the substance is transformed into the kinetic energy and potential energy of all its molecules. Thus, heat energy can be defined as the sum of the potential energy and kinetic energy of all the molecules of a substance. The total amount of heat energy is called enthalpy. If we supply some heat energy to a substance, the kinetic energy of its molecules increases. The temperature of a substance is directly proportional to the average kinetic energy of its molecules. Therefore, the temperature of a substance increases as the kinetic energy of its molecules increases. Conversely, if some heat energy is given out by a hot substance, the kinetic energy of its molecules decreases. As a result, the temperature of the substance also decreases. Thus, heat is the cause and temperature is the effect. Now let us consider 2 bodies, A and B, at different temperatures. That is, A is at a higher temperature than B. If they are kept in contact with each other, heat energy will flow from the body A to the body B till their temperatures are equal. The common temperature that they attain is called equilibrium temperature. Thus, temperature is the physical quantity that determines the direction of flow of heat energy. The amount of heat energy lost by the hot body is equal to the amount of heat energy gained by the cold body. At equilibrium temperature, the rate of flow of heat energy from one body to the other and back is the same. As a result, the temperature of the bodies remains constant. Remember that heat will always flow from a body at higher temperature to a body at lower temperature. The amount of heat energy transferred from one body to another is measured with different units in different systems. The branch of physics that deals with the measurement of heat energy is called calorimetry. Since heat is a form of energy, its SI unit is joule. In olden days, heat energy was measured in calories. Calorie is the CGS unit of heat energy. 1 calorie is defined as the quantity of heat energy required to change the temperature of 1 gram of water by 1 degree Celsius. That is, from 14.5 degrees Celsius to 15.5 degrees Celsius. However, calorie is too small unit to measure heat energy for practical purposes. Thus, kilocalorie is used to measure heat energy, which is the MKS unit of heat energy. Sometimes, kilocalorie is also written as calorie with C in uppercase. 1 kilocalorie is defined as the quantity of heat energy required to change the temperature of 1 kilogram of water by 1 degree Celsius. That is, from 14.5 degrees Celsius to 15.5 degrees Celsius. The different units of heat energy are related as 1 calorie is equal to 4.186 joule. 1 kilocalorie is equal to 1000 calorie, which is equal to 4186 joule. Let us consider 200 gram of water in a container at a temperature of 15 degrees Celsius and supply some heat to it. If 2000 calorie of heat energy is supplied to the water, then its temperature increases from 15 degrees Celsius to 25 degrees Celsius. To increase the temperature of 200 gram of water by 10 degrees Celsius, 2000 calorie of heat energy is required. Let us now consider 200 gram of water in another container at 15 degrees Celsius and supply heat energy to the water. If 4000 calorie of heat energy is supplied to the water, its temperature rises from 15 degrees Celsius to 35 degrees Celsius. To increase the temperature of 200 gram of water by 20 degrees Celsius, 4000 calorie of heat energy is required. As the amount of heat energy supplied increases, the rise in the temperature of the substance also increases. That is, the heat energy supplied is directly proportional to the change in temperature. Let's generalize this. If Q is the amount of heat energy supplied to a given mass of substance, then its temperature changes by delta T. Then Q is directly proportional to delta T. Let this be equation 1. Then, the amount of heat energy required to increase the temperature of a given mass of the substance by 1 degree Celsius is called its heat capacity. Heat capacity is denoted by C. Heat capacity C is equal to Q by delta T. Let this be equation 2. The SI unit for heat is Joule and for temperature is Kelvin. Thus, the SI unit of heat capacity is Joule per Kelvin. The unit generally used for heat capacity is calorie per degree Celsius. Let us now consider 400 gram of water in another container at a temperature of 15 degrees Celsius and supply heat energy to the water. If 4000 calorie of heat energy is supplied to the water, then its temperature increases from 15 degrees Celsius to 25 degrees Celsius. To increase the temperature of 400 gram of water by 10 degrees Celsius, 4000 calorie of heat energy is required. If we compare this with the first case, we can see that as the mass of the substance increases, the amount of heat energy required to change its temperature by the same extent also increases. That is, the heat energy supplied is directly proportional to the mass of the substance. If Q is the heat energy supplied and M is the mass of the substance, then Q is directly proportional to M. Let this be equation 3. From equation 1 and 3, Q is directly proportional to M into delta T. This can be written as Q is equal to Ms delta T, where S is the proportionality constant called specific heat capacity. Let this be equation 4. Specific heat capacity is defined as the amount of heat energy required per unit mass of the substance to change its temperature by 1 unit. From equation 4, specific heat capacity S is equal to 1 by M into Q by delta T. Let this be equation 5. The SI unit for specific heat capacity is Joule per kilogram per Kelvin. The general unit for specific heat capacity is calorie per gram per degree Celsius. We know that 1 calorie is equal to 4.2 joule and 1 kilogram is equal to 1000 gram. Hence, the relation between the general and SI unit for specific heat capacity is 1 calorie per gram per degree Celsius is equal to 4200 joule per kilogram per Kelvin. The specific heat capacity of a material is independent of its mass, change in temperature, and the heat energy supplied. It depends only on the nature of the material. Different materials have different specific heat capacities. The table here gives the values of specific heat capacities of different substances. By substituting equation 2 in equation 5, heat capacity and the specific heat capacity can be related as C is equal to M into S. The specific heat capacity of water is 1 calorie per gram per degree Celsius, which is equal to 4200 joule per kilogram per Kelvin. Due to the high specific heat capacity of water, it requires more heat energy to change its temperature. There are some advantages of the high specific heat capacity of water. Water is used as a coolant in car radiators. Because of its high specific heat capacity, water can absorb a large amount of heat energy produced by the engine without much increase in its temperature. It is also used in hot water packs for fermentation. Fermentation is prescribed by doctors to maintain moderate temperature of swollen body parts, which provides relief. In cold countries, water is used for internal heating of buildings. As it has high specific heat capacity, it can carry large amount of heat energy from the furnace to the rooms at moderate temperature. Wind cycles, land breeze, and sea breeze are also caused due to the high specific heat capacity of water. Let us discuss the formation of land and sea breezes. During the day, the sun shines equally on land and the sea. Sea water has higher specific heat capacity than land. Therefore, the rise in the temperature of the water is less, while the temperature of the land rises rapidly. Thus, the air above the land gets heated and the hot air rises up. As a result, the atmospheric pressure over the surface of the land decreases. The colder air from the surface of the sea then blows towards the land, giving rise to sea breeze. On the other hand, during the night, the land and the sea lose heat energy. Now, land has less specific heat capacity than sea water. Therefore, the temperature of the land falls more rapidly than that of the sea water. Thus, the air above the land becomes colder than the air above the sea. The warm air above the sea rises up, which causes a fall in the atmospheric pressure over the sea. The cold air from the surface of the land then blows towards the sea, giving rise to land breeze. Matter exists in three states: solids, liquids, and gases. The transition of matter from one state to another is called change of state. The change of state from solid to liquid is called melting. And from liquid to solid, it is called fusion. A change of state from liquid to gas is called boiling or vaporization. And from gas to liquid is called condensation. Consider a round bottom flask with a thermometer and steam outlet fixed through the cork. Place some ice cubes at -10 degrees centigrade in the flask and start heating. Now, let us observe the change in the temperature of the contents and plot a graph between temperature along the y-axis and time along the x-axis, as it is an independent quantity. Initially, we observe a rise in the temperature of the ice as it absorbs heat energy. This continues till the ice attains a temperature of 0 degrees Celsius. If we continue heating the flask, strangely, we don't observe any rise in the temperature in the ice cubes. But we can observe some of the ice cubes melting. This indicates the change of state of ice to water. And during this process, both solid ice and liquid water coexist. No change in the temperature is observed till the entire ice in the flask melts to water. That means, on absorbing heat, ice at 0 degrees Celsius converts to water at 0 degrees Celsius. The temperature at which the solid and liquid states of a substance are in thermal equilibrium with each other is called melting point. Thus, the melting point of ice is 0 degrees Celsius. In this case, the heat supplied is utilized to increase the internal energy of the substance. The amount of heat absorbed by a unit mass of a substance to convert it completely from one state to another state is called latent heat, usually denoted by L. The word latent means hidden and is derived from the Latin root word latentum, which means to lie hidden. Latent heat is a characteristic of the substance. If Q is the heat required to convert a substance of mass m completely from one state to another at a constant temperature, then Q is equal to the product of m and L, where L is the latent heat of the substance for that particular change of state. The latent heat in the case of solid to liquid transition is called latent heat of fusion, denoted by LF. If we continue heating the water in the flask, its temperature starts rising again and continues to rise to 100 degrees Celsius. As the water gets heated, first, the air that is dissolved in water forms small bubbles at the bottom of the container. After some time, steam bubbles form at the bottom of the flask and move upwards. As they reach the cooler water at the top, they condense and disappear. The process of bubbles of steam forming and reaching the surface intensifies, and we say that the water is boiling. At this point, once again we observe no change in the temperature of the water, even though the water changes to water vapor. Even if we continue heating, the temperature of the water remains constant, and the heat absorbed is used to change the state from liquid to gaseous state. The constant temperature at which the liquid and the vapor states of a substance coexist is called boiling point. The heat required to convert one unit mass of a substance completely from the liquid to gaseous state at its boiling point is called latent heat of vaporization and is denoted by LV. If the rate of heat supplied by the source is known, a temperature time graph can be converted into a temperature heat graph, which is usually called a heating curve. Some parts of the curve are parallel to the x-axis, and some of them are inclined. the inclined portions of the graph correspond to a particular state of the substance. The slopes of the inclined portions are not equal. This means a substance will have different specific heat capacities in different states. The temperatures corresponding to parallel portions of the graph correspond to melting and boiling points. The melting point and boiling point of a substance depends on pressure. If measured at standard atmospheric pressure, they are called normal melting point and normal boiling point. For example, the melting point of ice decreases with an increase in pressure. If a metallic wire with two masses tied to both ends is placed on a slab of ice, we observe it passing through the slab. As the wire exerts pressure, the ice beneath it melts. When the wire passes through, the water above the wire freezes once again. This phenomenon of refreezing is called regulation. In fact, ice skating is possible only because of regulation. When the skaters move on ice, due to the sharp wedges at the bottom of the skates, there is an increase in pressure on the ice, and due to this, the ice beneath melts below its normal melting point. This makes the motion of the skaters smooth and friction-free. The boiling point of water increases with an increase in pressure. To understand this, let us return to the experiment where water was heated in a round-bottomed flask. When the steam outlet is closed, the pressure inside the flask increases, and the boiling point of water also increases. Therefore, the water in the flask stops boiling after some time. After absorbing more heat, the temperature of the water increases to a new boiling point, and it starts boiling again. A pressure cooker works on this principle. When food is cooked in a pressure cooker, the pressure that builds in the cooker increases the boiling point of water to higher than normal. And the food in the cooker is cooked at a higher temperature than if it were cooked outside. This makes cooking quicker and cost-effective. Cooking is difficult in hill stations because at high altitudes, the atmospheric pressure is lower than normal. And as a result, the boiling point of water this changing the solid state ice, iodine, examples of such substances. Must be completely absorbed by the cold body. Even when more than two bodies are placed in a thermally insulated box, some bodies lose heat energy and other bodies gain heat energy. The total heat energy lost by the hot bodies must be completely absorbed by the cold bodies. This means when two or more bodies at different temperatures are brought into thermal contact, and if no heat is allowed to escape to the surroundings, then the total heat lost by the hot bodies must be equal to the total heat gained by the cold bodies. This is called the principle of calorimetry. Calorimetry is the science of measuring heat. Heat gained or lost by a body is expressed by the equation delta Q equals the product of M, S and delta T, where M is the mass of the body, S is the specific heat capacity of the body, and delta T is the change in temperature of the body. For example, an apple of mass 0.2 kilograms and specific heat capacity of 3640 joules per kilogram per Kelvin is placed in a refrigerator. If its temperature is changed from 30 degrees Celsius to 10 degrees Celsius, find the heat that flows out of the apple. Given that mass M equals to 0.2 kilograms, specific heat capacity S is equal to 3640 joules per kilogram per Kelvin. Change in temperature delta T is equal to 30 minus 10, which is equal to 20 degrees Celsius. Heat that flows out delta Q is equal to the product of M, S and delta T. Substituting these values and calculating, we get delta Q equal to 14,560 joules. In calorimetry experiments, a device known as a calorimeter is usually used to make heat measurements. A calorimeter consists of a small metallic vessel with a stirrer, and usually both are made of copper. The vessel is placed in a wooden box with insulating material surrounding the copper vessel in the box. This wooden box acts as a heat shield and reduces heat loss. There is a wooden lid on the top of the box, where there is a provision to place a thermometer and also to pass the stirrer through. Let us find the specific heat capacity of a solid using the principle of calorimetry. To do this, a Reynolds apparatus and a calorimeter are used. As we use water in the calorimeter, we need to take a solid that is denser than water and insoluble in water, say a metal ball. First, the calorimeter with stirrer is weighed using a physical balance. Let its mass be M1. We now weigh the material used in the activity, that is, the metal ball. Let its mass be M2. Pour sufficient water into the calorimeter. And then the mass of the calorimeter and water is found to be M3. Then mass of the water is equal to M3 minus M1. Note the temperature of the water. Let it be T1. Now, heat the metal ball in the steam chamber of Reynolds apparatus till the thermometer in the apparatus shows a steady reading for a few minutes. And let the temperature of the metal ball be T2. The wooden partition separating the steam chamber and the calorimeter provides thermal insulation to the calorimeter from the chamber, so that there is no transfer of heat from the chamber to the calorimeter. Now bring the calorimeter below the sliding base of the steam chamber and slide open the base of the chamber. Drop the metal ball into the water in the calorimeter and stir the mixture for some time. Then note the equilibrium temperature T3. Let the specific heat capacity of the copper metal ball and water be S1, S2 and S3 respectively. Here, heat is lost by the hot metal ball and gained by the cold calorimeter and water. Heat lost by the metal ball is equal to M2 into S2 into T2 minus T3. Heat gained by the calorimeter is equal to M1 into S1 into T3 minus T1. Heat gained by the water is equal to M3 minus M1 into S3 into T3 minus T1. Applying the principle of calorimetry, heat lost by a hot body is equal to the heat gained by a cold body, which is expressed as M2 into S2 into T2 minus T3 equals M1 into S1 into T3 minus T1 plus M3 minus M1 into S3 into T3 minus T1. On further simplifying, S2 equals M1 into S1 into T3 minus T1 plus M3 minus M1 into S3 into T3 minus T1 by M2 into T2 minus T3.